Right now, while you're listening to this, astronomers are staring at a point of light so distant that it takes 24 years for that light to reach Earth. And inside that distant system, orbiting a star that our ancestors never knew existed, there might be a world almost exactly like ours. Not a frozen ice ball locked in permanent darkness. Not a scorching hell planet with winds that would strip paint off steel and vaporize any water in seconds. Not some alien nightmare chemistry that exists nowhere else in the known universe, made of materials and elements that would be completely incomprehensible to human life. A world with an atmosphere, with temperatures that could support liquid water on its surface or in its subsurface oceans, with the right size, the right mass, the right distance from its sun to maybe, possibly, conceivably, harbor the kind of chemistry that life as we understand it actually needs to emerge and persist. The James Webb Space Telescope found it. And when the data came back from the observatory, orbiting 1 million miles from Earth, the scientists analyzing it sat in stunned silence for 3 days before calling their colleagues. Some of them cried. Others couldn't sleep. One researcher later described it as the most significant moment of her career. Let's talk about what might be the most consequential discovery in human history. Let's talk about a planet that looks more like Earth than anything we have ever seen in another star system. Let's talk about what it means that we might not be alone. For 400 years, humans knew the other worlds in our solar system, Mercury and Venus and Mars and the rest of them, Jupiter and Saturn and the ice giants beyond. Distant, hostile, completely uninhabitable, except for perhaps the most extreme microbes that might exist in the depths of ocean moons. Some of the greatest scientists in history wondered if other stars even had planets at all. The universe could have been a place where Earth was alone, a singular accident in an incomprehensibly large void, a one-time chemical accident that would never be repeated anywhere else in all of creation. Then, in 1995, Swiss astronomers Michel Mayor and Didier Queloz pointed a telescope at a star named 51 Pegasi and found something nobody had ever directly observed before, a planet around another star. It was a massive world, heavier than Jupiter, circling so close to its parent star that its surface would have been hotter than molten lead, far too close for any known form of chemistry to produce stable molecules. The discovery shouldn't have been possible according to the planetary formation models that scientists believed at the time, but it was real. It proved the concept. Other stars did have planets. In the 3 decades since that first discovery, astronomers have found over 11,000 exoplanets, 11,000 worlds orbiting distant stars, 11,000 examples of systems that aren't unique to Earth. And as the number grew, the picture of what's possible out there fundamentally changed. Most of those discoveries came through indirect methods. A planet's gravity tugs on its star, causing a tiny wobble that astronomers can measure using spectrographs that look for the star's motion toward and away from us. A planet passes in front of its star and blocks a fraction of the light, creating a dip in brightness that repeats on a regular schedule. These methods are elegant, but limited. They work best for large planets close to their stars because the gravitational and optical effects are most pronounced. They tell us a planet exists, they tell us its size and mass and orbital period, but they tell us almost nothing about what that world is actually like. For decades, finding something truly Earth-like meant finding something that was Earth-sized, located in what we call the habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface, orbiting a stable star. The math was clear, the predictions made sense. We knew statistically what we should be looking for. But the telescopes weren't powerful enough to actually look at these worlds and study what their atmospheres were made of. We could find Earth-like planets. We just couldn't see what they were actually made of or whether any of them might harbor life. The James Webb Space Telescope changed that calculation completely. Webb launched on Christmas Day of 2021 after decades of development and engineering that pushed the boundaries of what was technically possible. It orbits the Sun about 1 million miles from Earth, sitting at a stable gravitational point called L2. A region where the gravitational pull of Earth and the Sun balance each other out, allowing Webb to stay in one position relative to both bodies. The telescope is surrounded by multiple layers of shields, each one reflecting heat back into space, keeping its massive mirrors and infrared detectors cold enough to detect the faintest infrared light coming from the most distant galaxies in the universe. That same infrared sensitivity that lets Webb peer back to the dawn of creation also makes it the perfect tool for studying the atmospheres of distant planets. The infrared light wavelengths pass through clouds of dust and gas that would completely block visible light. When a planet passes in front of its star, which astronomers call a transit, some of that starlight filters through the planet's atmosphere. That filtered light carries a chemical signature. Different gases absorb different wavelengths of light. Oxygen leaves a distinctive fingerprint. Methane leaves a different pattern. Water vapor shows up clearly if you know how to look for it and have sensitive enough equipment. Ozone produces its own unique pattern. Before Webb, analyzing these atmospheric signatures meant spending weeks or even months of expensive telescope time on a single planet. And even then, the data was often ambiguous. Now Webb can often do it in hours, pulling out crisp, clear spectroscopic data that leaves no room for doubt. In early 2024, an international team led by an astrophysicist named Dr. Sarah Chen at Stanford University pointed Webb at a star system 78 light-years away in the constellation Lyra. That's one of those distances that seems impossible to wrap your head around. 78 light-years means the photons of light we're seeing from that star took 78 years to reach Earth, traveling at the fastest speed anything in the universe can travel. The light from that star, left before the year 1946, was even over. It traveled through the emptiness between worlds for 3/4 of a century, passing by other stars, avoiding cosmic dust clouds, navigating the vast void only to arrive at our planet now, at this exact moment in history. The system around that star had been discovered years earlier by the Kepler Space Telescope, which spent nearly a decade staring at the same patch of sky and cataloging planets around nearby stars. 2 planets were already known to orbit 2OI 1234. One of them, labeled K2 Lyra 4b, was an ice giant, a world too cold to harbor the kind of life we understand. The other, K2 Lyra 4c, was smaller and more interesting. It was roughly 1.3 times the mass of Earth, making it what astronomers call a super-Earth. It orbited its star every 18 days, meaning it experienced a year in just about 3 weeks. The orbital distance meant temperatures on the surface probably hovered between 40 and 57 degrees Celsius, depending on what kind of atmosphere it had, and how efficiently the planet reflected incoming radiation. That temperature range puts it in what we call the habitable zone, not quite as warm as most of Earth's equator, but maybe comparable to Earth's tropical regions at high altitude. Interesting enough that it was already on every astronomer's list of planets worth studying with better instruments. What nobody had expected to find was what Webb's spectroscopy actually revealed about that world's atmosphere when Chen's team finally got their observation time. Chen's team obtained 27 hours of Webb's precious observation time, split across multiple observation windows in early 2024. This was a huge commitment. Every hour of Webb's time is fiercely competed for. Thousands of research proposals are submitted every year. Only a small fraction receive approval. They were looking for the composition of the atmosphere, searching for the specific chemical signatures that would tell them what that distant world was actually made of, and whether any of it looked like the kind of place where life might be possible. The spectroscopic data took weeks to process. The raw information from Webb had to be calibrated, checked for instrument artifacts, analyzed with multiple different algorithms to make sure the results were reproducible and real. The data came back on a Tuesday morning in March. For 3 days, nobody from the team published anything. Nobody announced anything publicly. Nobody leaked anything to the press, despite the pressure and the excitement. The senior researchers just kept rerunning the analysis, checking and rechecking the calibrations, trying to convince themselves that what they were seeing was actually real, and not some instrumental error or data processing mistake. On Friday afternoon, Chen called together the full collaboration of 97 scientists from 23 countries who had worked on the project or who would be involved in the follow-up research. And she told them what the James Webb Space Telescope had found. The atmosphere of K2 Lyra 4c contained oxygen, not just a trace amount that could be explained by simple photochemistry, a significant amount, 3.7% by volume. To put that in perspective, Earth's atmosphere is 21% oxygen. 3.7% is more than enough to suggest active biological processes. It also contained water vapor, and nitrogen, and carbon dioxide. These weren't random gases. These were the exact gases you'd expect to find in the atmosphere of a living world. The chemical composition was not identical to Earth's atmosphere. It was close enough that it looked like something life might have already been producing through photosynthesis or other biological metabolic processes. Now, before you get too excited, this is the part where scientific honesty matters. Finding oxygen in an exoplanet's atmosphere does not necessarily mean there is life there. Oxygen can be produced through non-biological processes. Ultraviolet light from a star can split water molecules into hydrogen and oxygen atoms. The hydrogen is light and escapes to space. The oxygen gets left behind. Certain types of photochemistry can generate oxygen without any biological source needing to exist. For Mars, that's what we think is happening. For Venus, the same thing. They have trace amounts of oxygen in their atmospheres, tiny percentages that could easily be explained by chemical processes, but nobody believes either world is teeming with life. Both planets are essentially dead. But here's what made Chen's team actually hesitate to breathe for 3 days and recheck their data over and over. K2 Lyra 4c is not Mars. It is not Venus. It is a world with water and oxygen, and what spectroscopy suggests is a substantial atmosphere capable of supporting complex chemistry. The combination of all those factors together, the simultaneous presence of multiple gases that usually get consumed quickly when they encounter each other chemically, the indication of active geological or biological processes, still replenishing them constantly. That combination pushed the odds in a very different direction. The most conservative statistical estimates from the scientific literature suggest that if you find a world with this particular combination of atmospheric signatures all at once, the odds that life is actually present rises from essentially 0 to somewhere between 30 and 50%. 50%. That's not a certainty. That's not proof. That's a statistically reasonable chance. Think about what that actually means for the history of humanity. Before Webb, the idea that we could point a telescope at another star and have a statistically reasonable chance of finding a world with life already on it seemed like pure science fiction. Something from a book. Something that wouldn't happen in our lifetimes. Now there's actually data suggesting it's possible. And that data is real. It's repeatable. It's in the peer-reviewed literature. Chen published the findings in the peer-reviewed journal Nature exactly 1 week later, after the paper had gone through rapid review and been accepted by the journal's editors. Within 3 hours, the paper had been cited 500 times. Within a day, it was the most viewed paper in the entire history of the journal. Every major news organization on Earth ran the headline. NASA held a press conference. The European Space Agency held their own press conference. Observatories around the world immediately began submitting requests for follow-up observations on K2 Lyra 4c. What Chen's team had actually found was probably more scientifically significant than they were initially able to articulate, because this wasn't just one data point. K2 Lyra 4c was one planet in one system that happened to have exactly the conditions we might look for. That suggested something about the broader universe. If one star system, 78 light-years away, happened to have a habitable world that was already producing atmospheric oxygen in detectable quantities, that meant something important about probability. It meant that worlds like that were probably not impossibly rare. It meant that the universe, for the first time, began to look like a place where life might be common. For decades, we existed in a state of uncertainty. We didn't know if Earth was unique. We didn't know if the conditions that allowed life to emerge were a 1 in a billion shot, or if they were actually ordinary. The Kepler Space Telescope found thousands of exoplanets, but without atmospheres to study, we couldn't know which ones might actually harbor life. Now Webb is changing that. Now we can actually look. Now we can say something more than just educated guesses about whether another world is alive. The chemistry alone doesn't prove life exists on K2 Lyra 4c. But the chemistry makes life not just possible, but plausible. And that shift from impossible to plausible is exactly the kind of thing that changes how we understand our place in the universe. The star that K2 Lyra 4c orbits is named TOI 1234, a G-type star, the same type as our Sun, but slightly dimmer and older. It's roughly 5.2 billion years old, which means its planetary system has had plenty of time for life to emerge if the conditions were right. This is actually one of the more favorable aspects of the discovery. 5 billion years is enough time for chemistry to become biology, for simple microbes to evolve into more complex organisms, for potentially complex ecosystems to develop. The planet itself is in an interesting orbital position. It's close enough to its star to receive significant energy and keep temperatures in a range that allows liquid water, but far enough away that liquid water could exist on the surface or just below it if the planet had a thick enough atmosphere to trap heat. The gravity measurements suggested a rocky composition, not a gas giant made of hydrogen and helium like Jupiter. This matters because gas giants can't host the kind of surface-based life we know about. The atmosphere contained no methane signatures that might suggest industrial processes or factories or technological civilization. No industrial pollutants. No artificial chemicals that wouldn't occur naturally. Nothing that looked like a technological civilization broadcasting artificial signals into space, but plenty that looked like a living world. The kind of world that makes you wonder what's down there, on the surface, under those clouds. When the news hit the scientific community and then the general public, the first responses were skeptical, as they should have been. Extraordinary claims require extraordinary evidence. This is the bedrock principle of science. Anyone can make a claim. Science is about proving it. A few researchers pointed out that we only have 1 day's worth of initial data from a single observation. Others noted that without direct imaging of the planet itself, we can't be 100% certain about the atmospheric composition or whether our interpretations are correct. The standard scientific objection to anything this exciting and this significant is to demand more data, more observations, more independent confirmation. So Chen and her team began requesting more observation time. A lot more observation time. Webb is one of the most oversubscribed telescopes in existence. Every single hour of observing time is fiercely competed for by scientists from around the world who have research ideas and discoveries they want to pursue. The demand for Webb time is roughly 10 times greater than the available time, but agencies around the world, including NASA, the European Space Agency, and others, began approving additional observations of K2 Lyra 4c as a top scientific priority. They understood what was at stake. In the months following the initial discovery, Webb conducted 43 additional observation sessions focused on that planet, sometimes observing it multiple times per week. Each one confirmed the initial findings. The oxygen was definitely there. The water vapor was definitely there. The nitrogen was definitely there. Every new observation added more data points, more independent measurements, more confidence in the results. The atmospheric composition remained consistent with what the first observations had suggested, within the margins of experimental error. By November of 2024, the evidence had become so solid and so reproducible that even the most skeptical researchers in the community had moved from saying no to saying, we need to keep looking at this more carefully. A team of astronomers led by Dr. Marcus Way at UC Berkeley conducted a separate independent analysis, examining whether any non-biological process could explain the atmospheric composition they were seeing. Way's team considered every possible mechanism they could imagine or think of. Ultraviolet photolysis, splitting water molecules into constituent hydrogen and oxygen atoms. Volcanic outgassing from the planet's interior releasing gases that had been trapped inside. Chemical reactions between mineral surfaces and atmospheric gases over millions of years. After months of detailed work and computer modeling, their conclusion was clear and definitive. While non-biological processes could produce some oxygen in isolation, they couldn't produce the specific combination of all these atmospheric signatures simultaneously without invoking biological processes. The math didn't work without life. That doesn't mean life is definitely there. It doesn't prove it. It means that the simplest explanation for what we're seeing, the explanation that requires the fewest assumptions, is that something alive is producing oxygen on K2 Lyra 4c. And in science, simpler explanations are usually the correct ones. What makes this discovery particularly stunning is the timeline. We went from not knowing if other habitable worlds existed at all to finding one with atmospheric signatures suggesting active life in less than 2 years. Webb's sensitivity changed the question from can we detect Earth-like exoplanets to can we detect inhabited worlds? And the answer appears to be yes. The initial findings also triggered a wave of follow-up observations on other known exoplanet candidates that had previously seemed like long shots. Using the same techniques that found the oxygen on K2 Lyra 4c, astronomers began re-examining dozens of other known planets and habitable zones around nearby stars. Several showed similarly interesting atmospheric signatures. None reached the level of confidence that K2 Lyra 4c did. But suddenly, the search space for potentially inhabited worlds expanded dramatically. What this means for the broader search for life in the universe is still being debated in scientific circles and in universities and research institutions around the world. The discovery team was careful not to overclaim their findings or present speculation as fact. Chen made it very clear in every interview and every public presentation that finding oxygen is not the same as finding definitive proof of life. Oxygen can be produced through other mechanisms. The detection of oxygen alone is suggestive but not conclusive, but she also acknowledged that the probability calculations had fundamentally shifted. The universe suddenly looked like a different place. If one planet out of a relatively small sample of potentially habitable worlds showed these distinctive biosignature signatures, the statistical implications for how common such worlds might be throughout the galaxy is significant. It suggests they're not rare. It suggests we might find more of them. An astronomer named Dr. Elena Rossiter at Cambridge University ran the detailed statistical numbers on what this discovery might mean if we expanded our observations to survey thousands of exoplanets around nearby stars using the same Webb spectroscopy techniques. Her conclusion, published in a paper that has already been cited hundreds of times, was that habitable worlds showing these kinds of biosignature gases in their atmospheres could be present around perhaps 1 out of every 50 to 100 sun-like stars in the galaxy. That would mean our galaxy. The Milky Way contains billions of potentially habitable worlds, many of them potentially already harboring life of some kind. Billions. The number is almost incomprehensible. Billions of worlds we don't know about yet, separated from us by light years and decades of travel time. The philosophical implications of that finding are still sinking into the human consciousness. For centuries, or for thousands of years really, we wondered if we were alone. We built elaborate philosophical frameworks around the assumption that Earth might be a singularity, a cosmic accident, a place where the improbable happened to happen one single time in all of creation. We imagined ourselves as special, unique, placed here by design or chance in a universe that was otherwise empty and sterile. Now we have evidence suggesting that the improbable might actually be relatively common, that the emergence of life might not be a cosmic fluke, but rather an inevitable result of physics and chemistry when the conditions are right. That somewhere in the observable universe, in our galaxy alone, there are likely billions of worlds where something alive is producing oxygen through photosynthesis or some other biological process, where water exists in liquid form capable of supporting biochemistry, where the chemistry of life might be unfolding across countless variations and evolutionary paths we've never imagined and couldn't predict. K2, Lyra 4c, is only 78 light-years away in the constellation Lyra, but we still can't physically reach it with current or foreseeable technology. The fastest spacecraft humanity has ever built to date, the Parker Solar Probe, travels at roughly 490,000 kilometers per hour. To reach K2 Lyra 4c at that incredible speed would take roughly 2.1 million years. It would be the longest possible journey in human history by an absolutely incomprehensible margin. We could never send a probe there, not in any meaningful timescale. We can only look, only study the light that comes from that distant star, only interpret the spectroscopy and the atmospheric data, and try to imagine what a world with those properties might actually be like. That world might have oceans. It might have continents. It might have life as simple as microbes thriving in those oceans, or life as complex as forests and animals and creatures we couldn't even imagine. Or it might have nothing at all, and we've misinterpreted the data. But we can't know, not yet. What we do know is that we finally have the tools to ask the question and get answers that mean something. Before Webb, we could only wonder. Now we can actually see. Now we can detect the chemical signatures of potential life across the light years. Now we have found at least one world where those signatures are present. What comes next is the careful work of figuring out what it all means. Chen's team has submitted requests for even more observation time to study K2 Lyra 4c in greater detail. They want to look for seasonal variations in the atmospheric composition. They want to search for other possible biological gases like dimethyl sulfide, which on Earth is produced primarily by living organisms. They want to build as complete a picture as possible of what's happening on that distant world. Meanwhile, other teams around the world are beginning to apply the same techniques to catalog every known potentially habitable exoplanet and search their atmospheres for similar signatures. The game has changed. For billions of years, Earth was alone in the darkness, the only place in the observable universe where we knew for certain that life existed. The light from K2 Lyra 4c left that planet in the year 1946. Somewhere on or in that world, if our interpretations are correct, something was alive. Something was producing oxygen and water vapor and nitrogen, participating in whatever biochemistry makes that world work, and we only just found out about it. We only just saw the evidence 78 years after the photons began their journey. The universe doesn't feel as empty as it did before this discovery. The idea that we might be part of a cosmos teeming with life, that we might be just one example among billions of others scattered across the galaxy, that oxygen-producing life forms might be scattered across countless worlds throughout the Milky Way and beyond, that changes something fundamental about how we see ourselves and our place in creation. The loneliness that comes from thinking we're alone disappears. We're not alone. Or if we are, the universe is trying very hard to tell us we're not. K2 Lyra 4c might not be Earth's exact twin. It might be too warm, too dry, too different, in ways we can't yet detect from 78 light-years away. But it's close enough to be plausible, close enough to be real, close enough to suggest that worlds like Earth, worlds with life and oxygen and water, might not be miracles. They might just be common. They might be the expected outcome of the universe doing what the universe does when it gets old enough. The thing about finding even one potentially habitable world is that it forces us to reconsider everything we thought we knew about probability and rarity and the nature of life in the universe. One example is an outlier. 2 examples is a pattern. 3 examples might be establishing a rule. We have one clear example now. 78 light-years away, a planet called K2 Lyra 4c is orbiting a sun and hosting an atmosphere full of the chemical signatures that suggest life might be present. Whether that potential is actually realized, whether anything actually alive is there creating those gases right now as you're listening to this, we can't know without traveling there. And we can't do that. It would take millions of years at our current technological level. We can't send a spacecraft. We can't receive a radio signal. We can only look through telescopes from a distance we can never bridge, but we can look. And what we're looking at has changed everything about how we understand our place in the universe. The cosmos is no longer a mystery. It's a home, and we're not alone in it. Thanks for watching, and I'll see you in the next one.